Right, welcome back. So, after introducing the logarithmic Sobolev inequality last time, now I want to see how it relates to the heat equation and how it relates to Ricci flow. So, relation of log Sobolev inequality to the heat equation and to Ricci flow. And everything is, of course, based again on the properties of the heat kernel. So recall that rho x, y, and t and s on Euclidean space is given by 1 over 4 pi t minus s n over 2 e to the minus x minus y over 4 t minus s, where t greater than s is in R, and x and y are in Rn. And I wrote it deliberately in this way in order to show the symmetry in x and y, and also to some sense the antisymmetry in t and s, because this solves now the heat equation forwards with respect to t, and it solves it backwards with respect to s. Because of the symmetry in x and y, you can take the Laplacian either with respect to x and y, and you can hear that we are in over alpha because outside they are moving along. Now, the second equation here is sometimes called the adjoint or conjugate equation. The heat equation, and the main point is, of course, that if you take ddt of the integral of the product of two functions, one solving the equation and the other one the adjoint equation, then the ddt of the integral of their product remains zero. Now, the identity that we had already used last time, the integral identity that is crucial here is the fact that n over 2 times the integral of rho, the volume, and you can take x or y over Rn, is the same as the integral over x minus y squared divided by 4 t minus s squared. No, not squared, times rho volume over Rn. And the key point to observe here, which is of interest to us, this here is the logarithm of the heat kernel. So you can write this also as stating, since the integral of the heat kernel is equal to 1, normalized, you can also state this, that n over 2 is equal to, this is minus the logarithm, so we can write this as minus the integral over Rn of rho times the logarithm of, not quite rho, but rho normalized with this factor, rho times 4 pi t minus s to the n over 2. Volume. So you have this identity, and this now motivates the following definition. Put it here, so I have it right next to this formula. we say that for a function u on Rn, or on some Riemannian manifold, so if u on some Riemannian manifold is var positive function, if this is a probability measure, in other words, if the integral of u d mu g over mn is equal to 1, then we call the quantity n of g and u equal to minus integral u log u d mu g over mn, the entropy. And this is the there's no tau parameter in there, so this is the unnormalized entropy of u with respect to the metric G. And this is a concept that comes from thermodynamics and is related to the names of Boltzmann, Shannon, therefore also named Turing. Some people also call it the Nash entropy. Many people in mathematical physics involved in studying this entropy for probability measures U. Now, the normalized version, where you have the parameter tau also play a role, normalized entropy is given by let's call it n of g and let's call it f and tau to be the integral of oops. Let's take this to be unnormalized entropy, and then we subtract minus n over 2 times 1 plus the logarithm of 4 pi tau such where the relation between tau, f, and u is given by 1 over 4 pi tau to the n over 2 times e to the minus f is equal to u. So f is the negative logarithm of u up to this factor, so you can solve for f. And this means that f related to u is given by minus the logarithm of u times 4 pi tau to the n over 2. And then this quantity here becomes the integral of n over 2 minus u log of u times 4 pi tau n over 2 the volume with respect to the measure G, and then you see that this quantity here is chosen exactly such that in Euclidean space you get 0. So the entropy on Euclidean space and tau of delta of the function f, which in Euclidean space is any x minus y squared over 4 tau with respect to tau is identical to 0 for tau. Okay, and for all y. So this is the definition of the entropy, and the interesting question is now, or the justification for this entropy is now the behavior of this entropy under the heat equation. And let's do the computation first in Euclidean space. So now suppose that we have a positive function u greater than 0 is a positive solution of the backward, which is the adjoint heat equation. Let's do it first on Rn. Then we can compute what is the time derivative ddt of well, the time derivative of n of delta of u let's see, n of delta of u, and so this is ddt of just the, let's walk down, of just this term here, dt of minus integral u log u times 4 pi t minus t divided to the n over 2 dx over Rn, and so in this case the tau is the u, and the tau would be t minus t, right? And differentiating this, we get now from here, because we have the backward heat equation, so we have ddt of u is equal to minus Laplacian of u. Then we get from here one term Rn, which is plus Laplacian of u times the logarithm of the rescaled u. Dx. And then we get the term coming from here, minus integral Rn, the 1 over 4 pi difference into the constant in the logarithm goes away, so we get one term which is just Laplace u, and the other term gives a one minus sign from here, and another minus sign from the t minus t, so we get a minus n over 2, and then we get in the denominator a t minus t, and the thing multiplied by u dx. So we end up now doing an integration by parts here with minus integral over Rn of du squared over u. And from here, there's nothing from the integration by parts from the t term. And then from here we get a minus Laplacian. This is a minus, and then the Laplacian, actually this is 1 over u, this is actually plus Laplacian, but a minus from there, so there's right, so I can write it as minus Laplacian of u minus, you see, minus, yes, two minuses n over 2t minus t times u dx. This is what we get, and this can be now slightly arranged in two different ways. One way I can write this as a integral over Rn. One way to write it is the Laplacian of u over u minus u squared over u squared plus n over 2t minus t times u dx. This is one way of writing it. And then you notice that this can be written here as integral over Rn of the Laplacian of log u. Plus n over 2t minus t, and this is of course the Laplacian of the log of the heat kernel. So you can also write this as the Laplacian of logarithm of u divided by the heat kernel dx. And we've seen in another course of this, in another lecture of this course, that this quantity is non-negative. So this is greater or equal to 0, since the Hessian of log u over rho is greater or equal to 0. Remember, this was part of the differential Hanna. This expression is greater or equal to 0 was the differential version of the Hanna inequality. So here's a surprising relation between the entropy and the Harnack inequality that we had proven in a previous lecture, where we had seen that this trace, actually, of this inequality it certainly is positive, and this was exactly the expression that we used to prove a Harnack inequality for any positive solution of the heat equation, or Rn, or actually on any manifold of non-negative Ricci curvature. So with this here, we see that on any solution of the equation, this entropy is monotone. And this is one of the key principles, of course. The monotonicity of the entropy is one of the key principles of thermodynamics. Monotonicity of entropy and its relation to thermodynamics. On the other hand, I could throw away this integral over the Laplacian in this case, of course, because the integral over the Laplacian, if you have reasonable decay, the infinity, like integral of x squared times u bounded, all these quantities that come up, then you can throw away this term in view of integration by parts. So the other way to write this is that ddt of n of delta u and t minus t. In fact, I should have written here f, which is the term. I should have really written f here. The relation between this f and this u is again that u is equal to, in this unrescaled case, no, this is the rescaled case, so we have u equals 1 over 4 pi t minus t, n over 2 e to the minus f. Right? So this is the relation between this f and this u, and we can rewrite this term here then as minus integral of gradient log of u squared, and this is like the gradient of f squared minus n over 2t minus t and the whole thing times u dx. So this is another way of writing it. And this is now looking like the term in the logarithmic Sobolev inequality. So you get here a relation to the w functional. And in fact, when you write it in terms of the w functional, and you call this capital T minus t, I put it on another board, tau, then you will see the relation to the w function. So let's write this out slightly different. So let's try to express this last term here. So we call that the w functional with respect to some metric g and some function f and some scaling parameter tau was equal to the integral of tau times df squared plus scalar curvature plus f minus n du g for some Riemannian manifold with metric g, function f, and some function tau, and I forgot, of course, here, I forgot the e to the minus f. Okay. This was the W functional, and we can write, since we can write the n of G and F and tau as equal to the integral of n over 2 minus the integral of f times e to the minus f d mu g. F is the logarithm of u, and e to the minus f is the u. Then we can write the derivative of n delta f of tau, where we now have tau set tau equals t minus t, so that dd tau dt is equal to minus 1. Then this computation here can be seen as I pull the 1 over tau out, and then I get here the integral tau squared f squared minus plus minus n over 2 times u, and the u is equal to the minus f. And then this becomes equal to the w functional with minus 1 over tau times w functional of f of the standard metric f and tau, and this one here I just have to subtract. I have to subtract this again, so this is just like adding n of g, f, and tau. Okay, we get this formula. So, and we know this is because of our Harnack inequality, this whole thing in the Euclidean setting where u satisfies the backward heat equation, in this particular case is greater or equal to 0. Right, so it's a magic calculation that works in Rn, but even more magic is the fact that now the same thing goes through on a Riemannian manifold, provided the Riemannian manifold satisfies Ricci flow. So now in the next step, we have already set up the definitions, the entropy and the W functional. Here in this case, of course, the W functional, there is no scalar curvature. But we have to, but the definition is there. This comes from Perelman. And now he didn't motivate it with the Nash entropy. By the way, this is taken from the reference that I've given you, the notes of Peter Topping. A very good place to read up on this. I think this is the nicest way to motivate it, coming from the heat equation and looking at the very classical concept of entropy. You just differentiate the entropy, you come up in the natural way with the W functional. And now this W functional is the thing. If you, in general, add in this scalar curvature term, then it will now turn out that it fits together with Ricci flow. So in the next step, now consider a Riemannian manifold. With metric G of t, solving Ricci flow. So we have ddt of gij is equal to minus 2 times Rij. Rij is the Ricci curvature of G. And then our first question is, what is the adjoint equation to the heat equation? What is the adjoint equation to ddt of V equals Laplacian of V? This is, of course, the Laplacian with respect to the metric G of t. So we want to look at the adjoint equation. Adjoint means we want that ddt of V times u integral is equal to 0 if the u satisfies the adjoint equation. So now, obviously, the Laplacian is a self-adjoint operator on any Riemannian manifold. So, and we know what the adjoint of ddt usually is. So, we expect that the ansatz should be ddt of u is equal to minus Laplace u plus something. And the question is, what is this something? What is q? Well, we want that ddt of the integral of u times v times du g of t over mn is equal to 0 for any such configuration. Now just do the computation, so we get 0 equals integral over mn of Laplace v times u, and then we get plus v times ddt of u, and ddt of u is equal to minus Laplacian of u plus q. Q is what we want to find out. And then from the measure, we get minus r times u times v u g. So this is the extra term we have to take into account when finding the adjoint equation. And you see that now, doing an integration by parts twice, the Laplace v cancels the Laplace u term, so we end up with the integral over mn of v times q minus r times u. V times q minus r times u dvg. Right. So, and then it's clear what there's a v missing. So it's clear what q should be. Q should be equal to r times u. So the adjoint equation is the following. You take ddt of u equals minus Laplace u plus r times u. If we do that, then we get that these integrals of u times v remain constant. Okay, so now the claim is that if G satisfies Ricci flow and then U satisfies the adjoint heat equation, that then ddt of the normalized entropy produces on the right hand side exactly a functional which which relates to the W function. So we have to convince ourselves that this computation works. So let's first do it in the unnormalized case. And consider first the unnormalized entropy. We have n of g and u is equal to minus u log u du g over n, and we assume that ddt of u is equal to minus Laplace u plus r times u, and we have ddt of g equal to minus Ricci of g, which in particular means that ddt of d mu g is equal to minus r times d mu g. So computing this, we get ddt of n of g of u is equal to minus, and then I get from here minus Laplace u plus Ru times log of u, and then from this term here, 1 over u cancels, so I get minus Laplace u plus Ru, and then from the measure I get plus u log u times minus r d mu g. Now you see that the Ru log u log ur, this term here cancels with this one. The Laplacian, because it's a compact manifold or you have sufficient decay, then the Laplacian term will go away, and we are only left with the Laplacian u log u. This is a minus minus is plus. Doing an integration by parts gives a minus sign, gradient u squared over u. And then from here, you get an r times u with a minus sign, no, two minus signs. Oops, what? Yeah, so it's a plus sign here, plus Ru d mu g and n, which we can write as minus integral gradient of log of u squared plus r times u times d mu g over mn. And this in turn we can write as minus integral, and if we now write again u as e to the minus f, then this becomes minus gradient f squared plus r times e to the minus f d mu g over nn. And this function on the right hand side of f, Pellerman called the f function. He didn't motivate it this way, he just dropped it in the paper. So f of g to f is integral of df squared plus r times e to the minus f d mu g. Okay. And this is what you get in the unrescaled setting. And the point later is going to be that this quantity itself is going to be monotone and under Ricci flow, and therefore has a lower bound, giving us a lower bound on the change of the entropy. Now, the significance of this thing is also that it has come up in different contexts, like in quantum field theory. So, this quantity comes up also in the context of certain models in quantum field theory. And you should think of it like really the scalar curvature integral times some volume form, where now the volume form has an extra potential coming from F, and you also have an energy for this volume form e to the minus F. So you have sort of the classical energy that also leads to the Einstein equations on the one hand, and you have the energy of a scalar quantity that has to do with the volume form of the manifold. In physics, this here is of course the thing that leads to the Einstein tensor, and this thing here is what they call a dilaton. But I'm not going to go into this direction, except that Perelman apparently was aware of this physical interpretation also of these quantities. Okay, so now this quantity comes up if we look at the unnormalized entropy. Now, we can also do the corresponding computation showing that the W functional comes up if we do this in the normalized setting. Here is the W quantity. So these definitions remain. So to compute the evolution in the renormalized setting, and we call that n of g of u corresponding to f of tau is equal to, let's write it down again, n over 2, this is an n, minus integral of u log u times 4 pi tau to the n over 2 d mu g, and then where the tau is equal to capital T minus T, so that d tau dt is equal to minus 1. And then computing this with respect to t, dt of n of g u of t tau is equal to, and here we use, of course, again the ddtu equals minus Laplace u plus ru. And then we get exactly the same computation as in the Euclidean space and as in the unnormalized case. And you just have to be careful with the tau. So you get here minus integral the from u we get minus plus ru times log u times 4 pi tau to the n over 2. This is from here, and then minus Laplace u times log u 4 pi tau n over 2. This takes care of the derivative of this. Then let's take the measure. From the measure we get minus r times u times log u times 4 pi tau to the n over 2. You see immediately that these two terms cancel again. And then we still get, from differentiating this, we get plus Laplacian, minus Laplacian of u, which will integrate out to 0, and from here we get now, because d tau dt is minus 1, so we get minus n over 2, and this is minus tau, is t minus t, or tau I should write, minus n over 2 tau times u, and the whole thing d mu g. And then collecting this, we can pull out a minus 1 over tau, like we did in the Euclidean setting, and we end up, after the integration by parts here, with two minus signs. One integration by parts gives a one minus sign, which is out here, so we get gradient u squared over u from this term. And finally we get a minus, somewhere something is missing here. Here, I forgot something, minus the ddt of u, differentiating here, I got a ddt of u, and this of course gives a plus ru. So here I have a tau plus r u, an extra tau in here, minus n over 2 times u du g. And now I can rewrite this as minus 1 over tau integral over mn, and now I write writing this as in terms of df, ff again, we get tau df squared plus r. I put a u outside of everything, and I get here minus n over 2 times u right, and now we can again write this as minus 1 over tau as the integral over mn, as the here we can write this as a w functional of G, F, and tau plus the entropy of G, F, and tau, where we now have the relation between U and F given by this equation. Okay, so we have exactly the same formula as in Euclidean space if we define the W functional with the R in here. And this shows that we get again a lower bound on the evolution of the entropy if we have control on the W. Another point is important that we can right. So now all these computations would not be so useful if we cannot show that we have some control on the W along Ricci flow. Right? We have now seen that there's a beautiful relation between the adjoint heat equation and the entropy, and meaning the function U times log U. But it only becomes worthwhile if we can now get a lower bound on the W and or on the F. So now the beautiful thing that Perelman observed was that F and W themselves satisfy a monotonicity formula. And in some sense it is inspired from, nobody knows whether Perelman was discovering the connection to physics first or later, but there is a theorem in this quantum field theorem, quantum field theory, that says that this has a physical meaning itself of some kind of energy or entropy, which in the physical context could be seen as monotone. So if one knows that, then it is natural to hope that this quantity behaves monotone. Otherwise, it is in some sense magic. So here's the computation. Right, so now consider again the situation of Ricci flow on Mn. So we have ddt of Gij equals minus 2 Rij, which implies the evolution of the measure, and it implies that the inverse metric evolves by plus 2 Rij, indices raised. And we also want to consider the adjoint heat equation. And we have a parameter tau where we assume that this parameter tau behaves like capital T minus small t. Think of approaching a singularity at capital T where we want to find out something. So this parameter tau will go with minus 1. And then we want to see how the W functional and the F functional change. Now for that, I need to know how the little f changes, because then the computation becomes easier. So if we set f equals minus log of u times 4 pi tau to the n over 2, which means that u is equal to 1 over 4 pi tau to the minus n over 2 times e to the minus f, then an evolution equation for u translates into an evolution equation for f. So let's compute ddtf. You get minus 1 over u 4 pi tau to the n over 2 times ddt of this. So this gives us ddt of u is minus Laplacian u plus ru times 4 pi tau over n times 2. And then we get plus n over 2 times 4 pi tau to the n over 2 minus 1 times a minus sign from the ddt tau times 4 pi. Right? That's what we get. And on the other hand, the Laplacian of f is equal to di of minus 1 over u di of minus 1 over u diu. And there is no t term there. And then taking one more di, we get minus Laplacian over u plus gradient log u squared. So if I insert this in here, I get on the right hand side the tau factor cancels, so I have exactly this minus Laplacian of f. But then I get plus gradient log u squared, but log u is f, so I get plus gradient f squared on here, is this right? Yeah, and then I get from here, this term cancels, so I get minus r times u, and this takes care of this term, and those two terms on the board. So I'm just left now with n over, with a plus sign, n over 2 tau. And this is an evolution equation for f. Okay? So with this evolution equation for f, and the evolution equation for mu, and the evolution equation for the metric, and by the way, the evolution equation for the scalar curvature, remember, this was Laplacian r plus 2 times Ricci squared. it's clear now that with all these ingredients, you can compute ddt of the entropy and ddt of the W functional and ddt of the F functional of parallel. Okay, so all the ingredients are on the board. Now it becomes a long exercise to actually do the calculations. And I'll just do it for you in part for the F functional. So the monotonicity formula well, we just do the simpler case of f of g and little f is integral df squared plus r times e to the minus f d mu g. And in this case, we have e to the minus f equals u and ddt u equals minus Laplace u plus r. And if we don't have the tau parameter, then ddt f equals minus Laplace f plus gradient f squared minus r. I made a mistake. Right? There's no factor u here. There's no u. The u cancels out. So there's just an r. So here's r. Okay. So these are the formulae, and then so if you do notice that the f squared is of course g upper ij df dxi, in some coordinates df dxj. So the derivatives themselves don't depend on time if you fix the coordinate system locally, but the g upper ij depends on time because the measuring is involved. So in the and the other thing, a little later we will have again we will have to use the commutator identity. The Laplacian of the derivative of a function with lower index is the same as the derivative of the Laplacian of the function plus an extra term, which is exactly the Ricci curvature times the gradient of the function. So we notice these 2 points in the calculation, and then we compute that ddt of f of g of t f of t is equal to now from the first term we get let's split it up into 2 parts. Df squared plus r times e to the minus f d mu plus integral df squared plus r times ddt of this measure e to the minus f d mu. Okay? And ddt of e to the minus f d mu is from the f we get minus ddt f, which is plus Laplacian up here, and then minus df squared plus r, and from the times e to the minus f, and from here we get a minus r. So we get minus r e to the minus f d mu, which is equal to Laplace f minus df squared e to the minus f d mu. Okay, that's gives us the evolution of this term. And on the other hand, we get that ddt of df squared plus r. Let's do first the evolution of r. This is Laplacian of r plus 2 Ricci squared. And then from here, from the df squared, and using this formula, we get plus 2 Rij dif djf from the norm, and then we get from the two factors here 2 times dif times dj, and now I have to insert the evolution equation of f, which is minus Laplace f plus df squared minus r. Now, putting it together, you have to do then a couple of integrations by part. So I'm not doing the whole calculation, but you have to notice to integrate the appropriate terms by parts. For example, the term, you write that the term 2, there's one term where you have where are we? We get one term which is 2 dif dj of minus Laplacian f what is wrong? Yeah, this is not a dj, this is another I minus Laplacian f times e to the minus f d mu, right? There's going to be one such term. Now you write this as minus 2 integral dif, and then here you replace the derivatives, so you get the Laplacian of dif, and the error term is minus Ricci djf times e to the minus f d mu, and then you integrate this term by parts, So this gives you a plus 2 times the Hessian of f squared e to the minus f d mu. But you have to be careful, there's one derivative also going onto the minus f, so you get another term which gives you one minus sign from the integration by parts, one minus sign from the minus f, so you're left with a minus sign times integral dif d k dif dkf times e to the minus f d mu. So you get one such term, and you also have the Ricci term. So we have plus 2 times the Ricci curvature dif djf e to the minus f d mu. And minus is plus, right? And so you got 4 of them altogether. And the other thing we have to notice is also that you can that you have to use when you to get rid of Ricci terms, you have to use the fact that gradient I of Rij by the contracted Bianchi identity is gradient Jr. So the crucial terms to look for is you have the square of the second fundamental form, and you have the square of the Ricci tensor coming up here, both with a plus sign. And then you get cross terms when you now integrate one of these guys by parts. You get a Hessian term here, the djf e to the minus f can be written as minus dj of, right, so we got 2 of these terms from here, and we got 2 of these terms from there. So we can write the 4 terms Rij, dif, djf, e to the minus f. This is minus 4 times Rij dif dj of e to the minus f d mu g. All right. Now you can integrate by parts the dj, so this gives you plus 4 integral Rij di djf e to the minus f mu. And the dj, if it falls on the Rij with the contracted Bianchi identity, gives you a minus 2 times gradient IR, gradient IF, e to the minus f mu. On the other hand, you get a term from the Laplace R. When you integrate that by parts, you also get a gradient R term. And the claim is that, and here you have the mixed term, for the 2f squared and the 2 Ricci squared from here. So the claim is that all the other terms go away, and then with just gathering terms, maybe do one more integration by parts somewhere to see things cancel out, so you get ddt of script f of g of t, and the f of t turns out to be plus 2 times, what do you get? Yeah, 2 times integral of the Ricci tensor plus the Hessian of f squared e to the minus f into squared root of 2 0. This is magic monotonicity formula. And the question is, of course, in any of such monotonicity formula, what is the special case when you have equality? So, and you notice that equality is exactly the case where Rij is equal to minus Rijf. And this was a Ricci soliton. This was a translating Ricci soliton which just moves in the direction of the gradient of f. And that, of course, is a very, very special case. So we obviously found, or Perelman found, some deep relation here between the entropy and the monotonicity of the derivative of the entropy with equality on Ricci solitons. And that is a deep insight that will lead us to the estimate on non-collapsing. But to do that, you also have to look at the rescaled version, which is leading to the W functional and the monotonicity of the W functional, and that will be related to the shrinking solitons, just like this one was related to the translating solitons where there's no shrinking tau involved. And that's a good point to stop for today.